Thank you, Francisco. Thank you, everybody. Thank you for coming. I want you to think about everything that is surrounding us. Our clothes, the metals, the plastics, this building, all this energy which is surrounding us, all of that we extract it from nature. And we do it in a very unsustainable way. In just a few months, we take all the resources that Earth takes a whole year to produce. This is how we are treating our planet. This is the chemical industry. The transformation of metals, oil derivatives, water and gases in everything which is surrounding us. This is a major, major undertaking. Of course, we cannot continue to do that. And that means that we need to reinvent chemistry. We need to reinvent not just the science, the whole chemical industry. Is a major, major undertaking. But we can do that. I'm going to show you specific examples of how we can achieve a new kind of chemistry which has been designed from the very beginning so we can recover and reuse our materials. And there is a problem. The problem is that when we teach chemistry, we see, we say this is the science and industry of transformation, and we teach chemistry in that way. Like if resources will be limitless, and once we make the products, that's not our product, and that's not our problem. In fact, chemistry is all about increasing the yield of those transformations. That's not how nature works. Of course, in nature there are single steps. Of course, there are reactions. But every single reaction has been, I would not use the word design, let's say evolved, in a way that is going to be the reactant for the next step in a very efficient way. So today is all about building, imagine, and implement it, and at an economic way, a new kind of chemistry, circular chemistry, and that needs to be designed. And that was the topic actually of a recent article I wrote for El País about how to reinvent the whole industry of the country. By the way, in our countries, almost 1 million people work for this industry at 5% of our GDP. So it's a major contributor to our economy. That was also the subject of a recent editorial that I wrote for Angewandte Chemie, where I said we cannot continue to teach and implement chemistry like A plus B to obtain C, that is just extracting materials and producing products. We need to work more like nature and start using catalysts and enzymes so we can recover everything we produced. And this is a fantastic example how this is possible. Look, when we make plastics, we design plastic so they will last forever. Why? Because we want these chairs to be here for many years. So when we decide this plastic has been designed for life forever. Forever. Not like wood or not like paper, that needs to last forever. So now they are inventing a new generation of plastic, like these ones here, with these dynamic bonds, that with a simple treatment, this is with a sulfuric acid, the monomers of the plastic can dissolve, and then once you have the monomers, rebuild the plastic many, many times, because the plastic has been designed so they can be disassembled. Also, the ones that we have in our mobile phones, this high-density polyethylene, again, is designed to not having any breakpoints, so you cannot recycle that. It has been designed in that way. So now there are advances to include breakpoints in plastics, so just with methanol, you can recover in a quantitative manner the monomers and make these plastics once and again. So it's all about designing from the very beginning our molecules and processes so they can be recovered and reused, because we are not doing that currently. And again, I wrote about that for Scientific American, how we need to reinvent chemistry and start thinking from the very beginning, not at the end, not just recovering the plastics or the paper or the cans to recover them. Just keeping that in mind from the very beginning. But if there is one area, and I'm going to be talking about CO2, where we are seeing incredible things, is in CO2 conversion and in general, the use of light. This movie, it looks like a miracle. I'm going to explain what that thing is doing. That is just a metal sheet with two catalysts That's a water from a river, and just with sunlight, without electricity, we can split water and generate oxygen and hydrogen. That's photoelectrocatalysis, just with the sun getting enough energy without any solar cell directly from the sun to split water into hydrogen and oxygen. Now that is possible. Again, I wrote about this year, I contribute to Scientific American every year one article, and this year I choose to talk about sun power chemistry. And the reason for that is discoveries like this one. This is in Panasonic. They are using, again, just sunlight in a saturated solution of CO2 to produce formic acid. That is just fantastic. But now people can make many other things. This group here from the University of Toronto, and I just want to give you some specific advances of how these things now can be achieved, is actually transforming CO2 into ethylene. That's a very, very difficult molecule to make. CO2 is completely oxidized, very stable, it's like a rock. And just with electricity, these people is making ethylene, the monomer of a plastic. So now we can take CO2 from the atmosphere and transform it into the monomer to make our plastics, to make negative emissions, to take a problem and convert it into a solution. This group was improving that technology. That was from last year, and now this year, in 2 years' time, now they can transform CO2 into ethylene to 90% conversion. Now we are talking about business. This is CO2 into the monomer of how we make plastics at 90% conversion, just with electricity, with no chemicals, nothing else. This electricity, of course, should come from renewable sources. And again, I highlighted that idea, the fact that now we have new catalysts that allow us to transform CO2 in all kinds of things. That was actually quite simple molecules. You know, ethylene is great, very useful, but only 2 carbon atoms and no oxygen, not the kind of things we can find, for example, in biomass. But this group in Rutgers in New Jersey, actually from CO2 and water and sunlight, photosynthesis, are transforming this carbon into something much more complicated, like methyl glyoxal and 2,3-furanodiol. Now these molecules are really complicated. Imagine how difficult it is, just with a surface, nothing else, just a surface, transforming CO2 into these particular molecules, nothing else. And this is the cycle. I'm not going to go into the details, but just to show you that this is indeed a cycle, like the Krebs cycle I was showing you before, but here there are no enzymes, it's just a surface. In this case is nickel phosphide, and electricity, and CO2 is entering into these molecules, making it bigger and bigger and more complex, and now can you make these kind of crazy things with 4 carbon atoms and 4 oxygens and a double bond with a surface and electricity. These kind of things are amazing. Of course, people in the audience will be saying, yes, but these molecules done in this way will be very expensive to make, maybe a very low yields. No, these people from this university started a company, are selling these molecules at market price. Isn't that amazing? CO2 from the atmosphere, now making difficult molecules with no solvents, no enzymes, no nothing, just electricity, and selling them at a market price. This gives me an entry now to what I've been doing, because we are not transforming CO2 into new molecules, but my contribution also in catalysis is reducing the CO2 footprint of one of the major CO2 contributors, which are, of course, refineries. When I moved to MIT, I decided that I wanted to apply nanotechnology to oil refining. I know that sounds like water and oil, but it is possible. I'm going to show you how actually managed to do it. These hydrocarbons, these very bulky molecules, should go inside the pores of the catalyst, and now I'm going to show you a real movie that provides you a glimpse of how our technology produces these molecular highways, these channels that allow very bulky hydrocarbons to go through the structure of this catalyst, which is a microporous solid, so you can make more of the valuable products and less of the residues, significantly less CO2. I made that discovery at MIT. There I have all the resources, but I wanted to start a company, and I moved from beautiful New England to Oklahoma. In case you don't know Oklahoma, this is the Oklahoma I found. That's the kind of lab that I moved in. The first day we found the lab, it was like this, nothing like MIT. Why I moved to Oklahoma, it was because this person, Marvin Johnson, is a very important person for me. He retired from a major chemical company. He wanted to work with me, not cost, just because he enjoyed the technology and working with this crazy Spaniard on this technology. This guy has 250 patents in my field. So if I wanted to make sure that my technology could be a scale up and actually get it to the market, this was the guy. He was probably as crazy as I was at that time. Then, in a very humble way, with very limited resources, we were able to generate data that allow us to raise quite a significant amount of money. Then I moved back to the East Coast, in this case to New Jersey. We were able to produce or to build this pilot plant and make it all the way to a refinery. But just to give you an idea, a refinery consumes 5 tons of catalyst every single day. So the scale up here is very significant. But because of that, and this is the main conclusion, because there is so much CO2 produced in this industry, just by using our catalyst, we can reduce in 1.2 million tons of CO2 per year. And my technology is now commercial, is being commercialized by Grace, the main catalyst producers in the world. They are now selling it everywhere, and that reduced CO2 production very significantly. So science evolved so much is teaching, and I wanted to end by telling you a little bit of what we do at IUPAC. I'm going to start with a video. I hope you can listen to it, because I know what it comes to your mind when I say IUPAC. I don't know if you follow Crash Course. It's a very famous YouTube channel, and it's a very famous YouTuber. He actually teaches chemistry, so probably what you are going to be listening from him is what you have in mind when I say IUPAC. So yes, it's like 30 seconds. It's very short. Let's go.
There's some of you out there taking chemistry, feeling a little bit like there's an international body whose job is simply to make your life more difficult, to force you to cram tons of information into your head, to suck all the wonder and excitement out of learning about how the world works at this beautiful fundamental level of chemicals. You are not actually imagining this. That organization actually exists. It's called the International Union of Pure and Applied Chemists, or IUPAC, and really they're looking out for your best interest.
Well, it's really funny. The video is great, and I know that when we talk about IUPAC, people feel that our only mission is to make very difficult names and to control the periodic table, and we are like evil people there. And that's why I want to show you the actual picture of the people who is member of IUPAC, people who are really crazy about using chemistry for the benefit of humankind in so many different ways. Thanks to these people, for 100 years, we have been able to create a common language of chemistry. Yes, we have a common language, like the mathematicians. They feel they are better, but we also have our own language. And now we have also the data that allow us to know the solubility of all materials, the thermochemistry. If you go to space and want to know the atomic weight of beryllium, it's in our periodic table. It's the same beryllium in another galaxy than the one we have here. For us, climate change is a top priority. I hope I will be able to convey the sense of urgency we have with this issue. We organize conferences. The main conference on green chemistry, of course, is organized by IUPAC. We work with the United Nations. And next year we are celebrating the International Year of Basic Sciences for Sustainable Development. This is a great opportunity for everybody to join forces with basic sciences to end with climate change. We have 17 objectives and 118 solutions. Yes, there are 118 elements in the periodic table, so plenty of opportunities. So we need a new way to do chemistry, and we need all scientists from space to health to make sure that our planet is not dying before we reach to the moon. Thank you very much.